Okay. Welcome everyone to a second lecture of the number theory course. Today we'll go over GCD and LCM. So let's get started. So the greatest common divisor, you all heard of this, but it's abbreviated as GCD. Okay. Of two positive integers A and B. So here's the notation. GCD AB denotes the greatest common divisor of A and B. And you'll be seeing this notation a lot. It's the greatest positive integer such that n is both a factor of A and n is a factor of B. Yeah, we're using the same column. Yeah, I think it's called a column. So basically this means n is a factor of A, n is a factor of B. Okay. Then we have the least common multiple, which is denoted as LCM. And then the LCM of two positive integers is done like this. And it's the least positive integer n, such that n is both a multiple of A and B. So that means A must be a factor of n and B must be a factor of n. Note that it says least. If for the least common multiple, if it wasn't least, then there'll be a lot of numbers that satisfy n. Say with this must be the greatest positive integer. Okay. Okay, so this is not rigorous enough. Like you have, well, you know it. We don't know a rigorous way to show what does this mean. So we have an alternative definition. Yeah, this looks scary at first, but let's go over product notation first. Okay, so product notation is just, if we see in this is pi, this is capital pi, as in Greek. So it's called phi, and it's called the product notation. So you have your subscript here, n is equal to 1, which is also called the dummy variable. And then you also have your superscript, which is k, and this is the maximum value of n. So this means this is equal to, and we plug n equals 1, we get 1. We plug n equals 2, we get 2, and we go all the way to k. So we get 1 times 2 times 3 all the way to k, which is equal to k factorial. Let's do another one. N is equal to 1, do up to k. Let's do 2n plus 1. So that means this is equal to 2n plus 1, then we have 3, and then it's product notation. So we times, and then we do n equals 2. We plug n equals 2, we get 5. Then we did n equals 3, then we did 7, and all the way to 2k plus 1. So you might recognize this as the multiplication of odd numbers. So basically this is kind of like a double factorial, but we won't go, it's not shown much in number theory, so you don't need to know it. So more of a symbol that basically says, I think 7 double factorial is equal to 7 times 5 times 3 times 1, but no need to fret about this. It won't, it's very rare in number, it's very rare in competitions. So let's go here. For any two positive integers, we have last week's kind of notation for it. X is equal to a sub 1 to the power of m sub 1 times a sub 2 all the way. This is basically its prime factorization. And same, y also has its own prime factorization. And then such that for a sub I, comma b sub I prime, the GCD, oh yeah, this basically says that all these numbers are prime. So it's basically saying that this is its prime factorization. Then we did GCD x times y, p sub I, and then this is the in. So basically we're just finding p sub I, and it's in all this, every single number, and this is the intersection. notation. So I made some examples. So basically the union is basically two sets combined. Let's call this set A and set B. And we're trying to find A union B. Okay. So that means, so the union is basically every number covered in both of the sets. There's an easier way to visualize this actually. So you all heard of Venn diagrams, right? Okay, we have all the numbers in set A. Yeah, these are called set notation, and this is the set of A, and that's the set of B. So this is A, and this is B. So here we have the numbers 2, 3, and 5, and in B we have the numbers 2, 3, and 6. What goes in both A and B? Correct, 2 and 3 both here. Okay, and then we can add these. Okay. So basically that's what we have. The union is basically all the numbers in A. So all the numbers in A plus all the numbers in the circle of B, and note that this B includes this. And then you subtract the numbers in A union B, A intersection B actually. We'll get to that in a moment. So basically first A intersection B is basically an intersection of the both sets A and B. Since these two have, okay, never mind. Since A intersect B means all the numbers covered in both A and B. Since 2, 3, and 5 and 2, 3, and 6, A intersect B has the numbers 2 and 3, right? This is equal to A union B. So it's basically every single number in A and B. It doesn't matter if one has one number and the other doesn't. It's basically all the numbers covered in this Venn diagram, and each number is counted only once. That's the most important thing to remember. So, and then A intersection B on the other hand is basically, it just lists what numbers does A and B have in common. Since A and B have the numbers 2 and 3 in common, then A intersect B is going to have 2 and 3 common, 2 and 3 in its set. Okay. Now let's see the example. Let's go back to example. We're finding the union, basically all numbers covered in A and B counted only once. So it's 2, 3, 5, 2, 3, and 6. So 2, 3, and 5 covered here. Then we have 2, 3, but we already wrote it here, so we don't count that. And then we have 6. 6 is not in A, so we put it here. Okay. Now, intersection actually is a bit easier than union. It's basically listing what numbers do both of them have in common. So here 2 and 3 are common in both sets. So we like the set is equal to 2, 3, and that's A intersection B. And this is A union B. So back to a definition. Well, yeah, this will appear a lot in combinatorics, but it also appears sometimes in number theory, especially like just find a set of all real numbers or all the numbers. You sometimes have to use set notation to answer the question. Anyways, back to the question. GCD x, y is equal to this. This is basically covering since it's intersect. This is basically showing what of these primes do both x and y have in common. So we'll go to this example. Okay, so we'll go to this example. What we are finding, what primes do these two numbers, let's call this x, let's call this y, what the primes do these numbers have in common? So basically we have 2 cubed, 3 squared, and 5, then 2 to the power 4, 3 cubed, and 5. All these primes, well, except this, note that 5 to the power 0 is equal to 1. This was a trick question. So since 5 to the power of 0 is equal to 1, we can erase it from a prime factorization. Okay. So then the GCD, I mean, the primes they have in common are 2 and 3 again, right? So therefore, okay, so therefore PI is the set. So we can say PI is basically, this is the in, so PI is basically the intersection, which is 2, 3. This basically means it is in. So PI is either 2 or PI is either 3. Then that's a bottom part, that's a subscript. So like this. And what number goes here to find it. And there's sometimes when there's not a superscript here. So that means it's and that's usually when we have this. So that's basically this. We only have to count it when PI is equal to 2 or PI is equal to 3. So these two are only dummy variables we had to plug in. Then we have P sub I, that's a dummy variable, to the power of the minimum of M sub I, and N sub I. So P sub I to the power of min, and then min sounds like minimum, right? Well, this is exactly what this notation does. Min basically finds the smallest number. So min 2, 3. The minimum of it is 2 because 2 is the smaller number, right? So we are finding the smallest of this. Okay. And then M sub I correlates to the P sub I. So if P sub I is 2, then we have P sub 2 to a power of M sub 2. Well, basically, let's go back here. Okay, so we are finding P sub I is and then I forgot to say this, but to make it less confusing, since this is, we are letting this be A1, A2, A3. We are letting this be B1 and B2, right? So that means 2 is either A1 or B1. We'll let that be A1. And 3 is basically equal to A2, right? So that means we can write this as PI is in A1, A sub 1. It can be either A sub 1 or it can be A sub 2, right? So A sub 1 to the power of, and since I is equal to 1, we did minimum M sub 1. So let's just put equal sign. Then let's write this clearer. P sub I is equal to either A sub 1 or A sub 2, and we have P sub I min M sub I, N sub I. Then we have we don't need like that. We can, let's first take this case when P sub I is equal to A sub 1. Then by substituting, we did A sub 1, and then I is equal to 1, right? I is equal to 1 because the subscript of this is 1. And we open a box, and since I is equal to 1, we have N1, N1. Okay, so I didn't say this, but this is equal to M1. This power is equal to M2. This power is equal to M3. And this power is equal to N sub 1. This power is equal to N sub 2. Okay, so then what's the minimum between this? This power is 3 and this per is 4, which is smaller, right? So we can write this as m sub 1 is 3, n sub 1 is 4. The small number is 3, right? So we did a sub 1 to the power of 3. And guess what? A sub 1 is 2. And a sub 1 is also equal to b sub 1. So we can write it like that. 2 cubed. Okay. And then that's only the first number. Remember, we also had to try a sub 2, right? Times a sub 2 case. Okay. Just make it correct. For space reasons, I didn't add a sub 2 because we'll be kind of running out of space. And then we can write it here though. We have to find a case where a sub 2 I is equal to minimum m sub 2, comma n sub 2. And then a sub 2 is equal to 3, right? 3 to the power of the minimum m sub 2. M sub 2 is 2. And then n sub 2 is 3. And then the minimum is 2, right? So 3, 2. Therefore, we did a sub 1 and a sub 2. So we have 2, 3 times. Yeah. So that means times 2, 3. So a GCD of, we let these numbers be x and y, right? The GCD of this is equal to 2 cubed times 3 cubed. So basically, let's find a better way to write it. You can't just write this whole formula in the middle of a math contest. So what you basically do is write a prime factorization, and then you find for each small prime, we check both of them, we compare. First, we see if both of the primes showing both of the numbers. If so, then we check which has the smallest power. So GCD, you can merge this. GCD, smallest power. So we check for the smallest power. And if we find, let's say this is the smallest power, we write it down in a GCD. Let's check the next one. 3 is both there, right? So we check the smallest one. This is small yet again. So it is 3 squared. And then what about 5? This has 1 power of 5, but this does not, right? So we don't write 5 here. Okay, so that's basically it. Let's I think we should erase this so we can do the LCM, right? I should erase that. Yeah, so basically it seems a little confusing at first, but I think my explanation of just now should probably help. And you should remember this. It makes it a lot easier. So GCD is, well, it's kind of weird because G stands for greatest and you're finding the smallest. So it's out of intuition, right? Anyways, so that's basically how you find the GCD. Now we find the LCM. LCM is equal to P sub I, and this time we are finding the union. You know, we already said what the union was, right? So basically this time we are finding the union, and this time it's a maximum instead of minimum. It's a maximum. So let's just quickly do this since we have a lot of examples. So basically we write this down. P sub I, the union is 2, 3, 5. And since 2 and 3 are already written here and they have nothing else, we have P sub I is equal to 2, 3, 5. And this is equal to P sub I is equal to A1, B1, and C sub 1. Wait, sorry, A sub 2 and A sub 3. Then A sub 2, A sub 3. Okay, and then we have P sub 1 to the power of maximum. This is basically finding the maximum number. M sub I, N sub I. Oh, I tell you, it's basically 2, 4, then 3 cubed. Okay, And this is basically equal to, we check a sub 1, we check a sub 1 max, and then m sub 1 is equal to 3, n sub 1 is equal to 4, right? Then we do times a sub 2 max 2 comma 3, and then 3 is the biggest, 4 is the biggest. And then for a sub 3 here, you have 1 power here, 1 power of 5, and then there are 0 powers of 5, right? There are 0 powers of 5 because it's not that. So 1 is the biggest. And when we equal this, a sub 1 is equal to 2, the max is 4, times a sub 2 is equal to 3, the maximum is 3, and then a sub 3 is equal to 5, so it's on here. Then the maximum is 1. And that's basically a LCM. So that's basically how this works. I'm trying not to take too much time since we have a good amount of examples to cover as well. So hopefully you understand under this notation. Hopefully you understand the intersection and union. Okay. And then we went through this last week, but here's a review. And this is a different definition of it. Last week, I don't think we covered GCD. So this is basically a better way to say it, I guess. Relatory prime, yeah, I also forgot, or co-prime. Both of them are correct ways to say it, co-prime. Relatory prime, two integers a comma b are known as relatively prime if and only if GCD a comma b is equal to 1. Basically, this is saying that if the GCD is 1, that means they don't have any factors in common. Since like GCD 2 comma 3, then we have 2 comma 1 here, 3 comma 1. And we are supposed to find the intersection, right? The intersection, they have nothing in common. So first we have to find the intersection of the primes. There's nothing in common for our primes. So we can't check the powers. So basically 2 and 3 are not the same. They don't have anything in common. So the answer will be 1. Okay. So that means this is relatively prime. 2 and 3 are relatively prime. Okay. Okay, now we got a nifty theorem here that's really going to be really helpful. Basically, it says for any two positive integers a and b, GCD a and b times LCM a and b is equal to a times b itself. But the proof is left as an exercise, but I found a pretty new proof here that I like to share, and it's pretty good proof as well. The other proof basically makes you have to go back and write all this out and then multiply it, and I think that'll take a while, so I found a simpler one. So let the C is equal to GCD A comma B. So C is basically this number as we did an output, right? Then we have A is equal to CX and B is equal to C times Y, right? Why is this true? Because of, well, we can use proposition 2.7, but let's assume that we don't know this yet. So we can say that since this is true, A is equal to CX, B is equal to CY. Now we are finding what factors in the GC, we find what factors do they have in common. C is both shown here, right? Right? So that means this can be equal to GCD X comma Y. And this basically means, in other words, C is a factor of A and B because C is a factor of CX and CY because the CX and CY are divisible. So that means we can write this as basically we can write A is equal to CX and B is equal to CY because this is the GCD, right? And for the GCD, we all know that GCD A comma B must be a factor of A and must be a factor of B. That's basically what the GCD says, greatest common divisor, right? So then A is equal to CX, B is equal to CY. Then we have X and Y are co-prime by the definition of GCD. GCD stands for the greatest, not any number. It's the greatest common divisor. Okay, so that basically means if C is equal to GCD A comma B, that means, and if we let A is equal to CX and B is equal to CY and take C out, that means we that reminder, we basically that C GCD X comma Y, and we know that C GCD X comma Y should be equal to GCD AB, since this is equal to GCD AB and this is equal to C times GCD XY, right? So then, since substituting back C, we get GCD XY is equal to GCD A comma B by C, and C is equal to GCD A comma B. So we get GCD A comma B. Strike this out. GCD X comma Y is equal to 1, right? Yeah. So therefore, these are coprime. It's also, you can just use intuition, right? Since we already said C is equal to GCD A comma B, and we also let these variables be it. We never, if X and Y are not coprime, then there'll be another factor. There'll be another factor times C, but we only said it's C. So therefore, they are coprime. Okay. So let's let this as lemma 1. We'll say this as 1 because we'll use it later. Then let's see the LCM. LCM on the other hand, LCM A comma B is equal to LCM CX by time comma CY because of this. Then we can also do the same actually. It's basically the same. LCM is the union. These two are already, yeah, LCM is the union. We can take the C out because it's in the union. So C times LCM X comma Y. But by lemma 1, we know that X and Y are coprime. So it means they don't share any factors. So if we take the union, of this, we did the set X and we did the set Y, because they don't have anything in common. They don't have any factors in common. So it's basically everything in X and everything in Y. And also I should be writing it as X, the set, but yeah. So all the numbers in, so it's a set of all the numbers in X and all the numbers in Y. And they don't share anything, so we don't have to take any numbers out. So then that means we have LCM X comma Y equal X times Y, right? Think for example, since it's coprime, LCM of 2 and 3 is 6, and 6 is equal to 2 times 3, right? That's why. And then since by 1 this is equal to XY, we get C times X times Y. Then, oh wait, did we write the GCD? Yeah, we write GCD A comma B, B, C. So then we multiply these two, GCD A comma B is equal to C times LCM A comma B is equal to CXY. Multiplying them, we get C squared X times X times Y. And this part is clever. So you know that C times C is equal to C squared. We put one C with X, the other C with Y. So we get CX times CY. And then by our definitions here, A is equal to CX, right? So then this becomes A and this becomes B, and we did A comma B part here. So that's basically a proof. GCD A comma B times LCM A comma B is equal to A comma B. I mean A times B. Okay. And in proposition, we just proved it in the last. We just proved it here. So, and it's also pretty easy to prove, and you can just plug in numbers and see that how it works. And then if you want to prove it, and then we also had to note this restriction after you put, you should be easy. Then we should notice 2 consecutive numbers are always relatively prime. This uses modular arithmetic to prove it actually, but I think which we'll go later in the lectures. The best method is to prove it using modular arithmetic. But basically we know n plus n comma n plus 1. We can solve it using the Euclidean algorithm, which we are about to teach now. Yeah, modular arithmetic, we are starting in next week. We can try to prove this next week after teach, but we can also prove it using the Euclidean algorithm, which we are about to learn now. For any positive integers m and n, GCD m comma n is equal to GCD m comma the absolute value. This basically means the positive. So all heard of it before. 2 minus 3 is equal to, with these signs around, with a now 1, it basically removes the sign. So we get 1. Okay, equals GCD n comma n m minus absolute value m minus n. Okay. So without loss of this stands for without loss of generality. In fact, it's just assuming that m is greater than n. We can also prove if n is greater than m using the exact same proof by flipping the variables. So we are allowed to log this. Then say we have some prime is divisible by both m and n. So p is divisible by m, p is the factor of n. So let m is equal to p times m prime. So this m prime is not equal to m. This is a different variable itself. And then n is equal to p times n prime. Right? For positive integers. Okay. For positive integers m prime and n prime. So, but note that we have p is divisible by p times n prime minus n prime, right? Because well, it's actually pretty simple because we are just substituting this. So, and we already said that p is a factor of m and p is a factor of n. So this would make sense. Then we have p is a factor of m minus n, right? Right? Which means that any prime factor that divides both m and n divides m comma n. So any prime factor, note if we say prime, that divides both m and n divides m minus n, right? Because of this. Next, we have to show that we can't have GCD m comma n minus n is greater than GCD m comma n, right? This is actually pretty easy because we know that GCD m comma m minus n by proposition 2.7. What is it? Yeah, it's basically this, right? Right. So we can't have, this is because GCD m comma m minus n is a factor of m, right? By the definition of the greatest common divisor, basically. Then now we have to prove that p can't be equal to GCD m comma n, right? So let's assume that, and let's use the proof by contradiction. So assume that this is true, p is equal to GCD m comma n, but we have m prime and m prime are relatively prime, as we said before. We already said that this can't be true as this is a prime, right? So m prime and n prime are relatively prime, which means m prime and n prime contain no prime factors in m or n. Therefore, we must have GC m comma m minus n is equal to p, right? And then this is true. I believe this proof is a little bit confusing for people who started, so you can always review it in the handout. And for now, it's not required to like fully know the proof, as long as you understand what we mean. So we're just saying that GCD 6, 2 can also be equal to GCD 6 and an absolute value 6 minus 2, which is equal to GCD 6, 4. And then once again, GCD 6, 2 can also be written as, you can also write it as n, this is n, right? GCD 2, m minus n again. All of them are acceptable ways to write it. So this gives us GCD 2, 4. and these are equal. So GCD 6.4 is equal to GCD 2.4. And then this is a generalized Euclidean algorithm. It's basically applying this again and again. So it's pretty easy to prove. So we can leave it as an exercise if you want. Okay, so it's basically saying GCD m comma n is equal to GCD m comma n minus kn. Oh, and then we have to add that kn must at all times be less than m, or else we'll have a negative value. And oh, I think we can have negative values, but now let's assume that we have to keep. Well, if the point is the negative value, then we have a most likely a negative GCD, and then yeah, it's pretty confusing. So kn must be less than m. Okay. So in other words, just to a high number, GCD 8,2 can be equal to GCD. Yeah, as it says, it's positive. 8,8 minus 2. It can also be GCD is equal to 8,8 minus let's say k is equal to 2 times 2, and g is equal to GCD 8,8 minus 3 times 2. Right? You can use order of operations to simplify that. Okay? That's basically what this says. Now it's 1.3 CST, so let's start doing some examples. Let's go through an easy one right now. Find a GCD and LCM of 1,536 and 1,764. This is intended to not be using the Euclidean algorithm. The next example is, so let's use the basic definition, what I first taught. So first we apply and factorize this. For simplicity's sake, I'll just write it down so we don't spend 5 minutes dividing all possible numbers under the square root of 1,536. So basically, this is equal to 2 to the power of 9 times 3, and you can try it with your calculator. And then 1,764 is equal to 2 squared, 3 squared, and 7 squared. Now for GCD, as we said, GCD is smallest power. First, we check the union. This is common, this is common, this is common. Right? And then which has the smallest power? This has the smallest power. So we like 2 squared. And then this has the smallest power. Then we have 3, 1. And then 7 is only showed here, not here. So we don't like 7. Okay, so the GCD should be 12. Yeah, let's check if it was correct. Okay, and then for LCM, we do about the opposite. So we find for 2, maximum power is 29. And for 3, maximum power is 3 squared. And then for LCM, we find a union. So we include 7 because it was, even though if it's not written here, it's still here. So we can write it down. And then this is the maximum, since here it's a 0 times 7 squared. And then I'll save time for the multiplication. And we'll just say it's 225,792. Most math competitions won't ask questions like this, as it takes a while to multiply stuff. Well, they can ask you for the GCD, but the LCM will be pretty bashy to solve. Okay, this is a problem we can use the Euclidean algorithm, and this requires polynomial factorization. So don't worry if you don't know that yet. We can walk through it. I think most of you can. Oh, it's cubic. Yeah, most of you know. I think you all know how to factor quadratics, but this is cubic. So find all positive integers case such that there exists at least one positive integer n satisfying GCD this expression, this expression is equal to k. Okay, let's see where we should start. I think a best way to start, just seeing if I made a mistake. Okay, I think the best way to start is factoring stuff. So factoring always, let's start factoring this expression first. So when we factor for cubics, usually we just try random, small numbers at first. So let's try n is equal to 1. Then we have 3 minus 8, 5 plus 3 is equal to -2 is equal to 0. So therefore, by the remainder theorem, we that n minus 1 is divisible of this. Okay, and then we do some long division. So if we divide this, I can also use synthetic, but I'm not as good with that. And synthetic division only works when this is basically what's the word? Yeah, when this is basically a linear expression. So 3 squared, 3 cubed, 5n squared plus 3n plus 5n minus 5n squared plus 5n is equal to -2n plus 2, which is equal to -2n, and then we have no remainder if we multiply. So then this is a quadratic. You all know how to factor it. We just use the box method. Just true. 4. Yeah. So then we have n minus 1 times n minus 2 times 3n plus 1. And then by the remainder theorem yet again, n can the factors of 1, 2, and 1 by 3, but that's not a point for discussion. Since we don't have, move this out for now. Okay, and then let's factor the next one. Factoring, we can quickly see that n is equal to 1 works here, right? So, and then let's save your time. This is a cubic DC. When we divide, we get n minus 1 times n minus 2, this time 3n plus 2. So basically, we are supposed to be finding GCD of n minus 1, n minus 2, 3n plus 1 equals, comma 3 n plus 2, n minus 1, n minus 2. And then right by the proposition 2.7, we know that this is equal to n minus 1, times n minus 2 GCD 3n plus 1, 3n plus 2. Now note that, yeah, we are saying that this is a consecutive number, right? If we plug in, we know that's a consecutive number, and this fact, what was it? Yeah. Fact 1 and 2 consecutive numbers are obviously relatively prime, right? And then we know that this is prime. These two are consecutive, right? So therefore they're relatively prime, and then the GCD of the relatively prime numbers is 1. So that is basically a GCD of the expression. So now we do the answer. This is equal to k, since I wrote here. So this is equal to k, right? K is equal to n minus 1 times n minus 2. That's the answer. Initially, we thought it was going to be all the triangular numbers, but it wasn't divisible by 2. So that's basically the best way we can write this as. Okay, what's next? Okay, find all pairs of positive integers m, n such as LCM of m, n is equal to 3 times the GCD of m, n. Okay, and we are finding all pairs of positive integers m, n, right? Okay, so let's use the formula mn is equal to LCM. This is what most people are inclined to do. Let's try this method. GCD m, n. Okay, then we have mn is equal to 3 GCD m, n squared, right? Well, What do you think? What are we supposed to do here now? Right, this is a little bit confusing. As we have mn is equal to 3 GCD m comma n squared. So let's see. So basically, we can rewrite this. Well, we can rewrite this as, sorry. So let's assume that that's a prime. Let's just say and it's not working. GCD m comma n is equal to, well, let's read it. Now what's next? You have a multiplicative GCD expression like this. This latex is much better. Let's pause it here. So we basically have 3 GCD of m comma n squared is equal to mn, right? So let's say that we have a prime factor of GCD m comma n. Okay, so that means let's say that the prime is p. So let's say the prime is p, and then let's say AP is equal to m, and then now and BP is equal to n, right? Then what we have, well, then it seems that, we have a plus b. Well, I think I made a mistake here. I'm sorry. Well, basically, I am pretty sure I made a mistake. So I think I made a typo. Sorry. So basically, let's move this here. And then I got another. Well, this is actually uses a lot of, well, the motivation of this is going to be pretty hard to understand. This is, so I'll paste it here. So let's assume that we have some prime factor p of GCD m comma n. So we are not saying that p, we are basically saying p is divisible by GCD m comma n. And let's assume I'll use a better variable this time. Let's say it takes, say, p sub n m times in m, and then let's say it appears p sub n times in n. So I'm pretty sure I'm doing, oh, then it seems that p sub n plus p sub n times, right? Because if it appears, if the p sub n times the p appears in m, and p sub m times p appears in m, I think we are supposed to use exponent. Okay, and then we have p sub n plus p sub n times in n. Well, basically we are turning multiplication addition, right? We're just saying that if m has a p sub m to the power of 3, p sub n to the power of 4, then in mn, when we multiply these two, it appears 7 times. So p sub n factors in mn. Okay, so that means for the GCD, then we have minimum p sub m comma p sub n times in the GCD. GCD has how many times factors? P to the power of min prime, min p sub n p sub n. So basically what we did here, let's say that we have prime factor P of GCD m comma n, and and since using the part that P using the definition of GCD, we're saying that it seems it has P sub n times in m, because that should be at least one. So let's say m is equal to something times P to the power of m P sub n. So it's part of its prime factorization. Let's see what we're supposed to do next. Thus, we have minimum P sub m comma P sub n is equal to P sub m plus P sub n. Okay, so that's basically an equation. That's how we got it. So since we're using the fact that in particular, if P is not equal to 3, let's assume P is not equal to 3, then it appears at least this much times in the GCD. So twice of that, 2 times that is equal to P sub n plus P sub n. Okay. So by inspection, it seems that we must have P sub n is equal to P sub n. So that means we'll have 2 P sub n. Yeah, it's basically kind of like circular reasoning. So this is equal. So this is equal. Then we have 2 P sub m equal P sub m plus P sub n. As the minimum of 2 equals thing, it's either this or this. And then we have P sub n equals P sub n again. Okay. So that's basically, we're just plugging in random values, and we can assume if both of these are equal, then that this equation is true, right? So basically we write P sub n is equal to P sub n. Now, now we have to assume that P is equal to 3. What if P is equal to 3, right? Well, if P is equal to 3, let's say that in M, let's say 3 appears A times something else. And then let's say in N, 3 appears B times, and then times something else. Then what do we have? Then we have 2, then for this equation, then we have 2 minimum A comma B, right? Plus 1 is equal to A plus B. Basically the same as this, but we have to add 1, right? Since P is equal to 3 and we have the LCM. Well, we basically have basically this, right? Then once again we do some inspection, and this time I'm pretty sure that if we assume that A is less than or equal to B, then we must have B minus A equals 1. Then when you try this out, A is equal to B minus 1, then the minimum is 2B minus 2 equals A plus B, and then B is equal to A. B is equal to, another mistake. So basically A is equal to B minus 1, then 2B minus 1, I forgot to do plus. A plus B is equal to B equals A plus 1, and that's basically this. So what is the answer? Basically we're going to use some actual lifting the exponent formation, notation, because you learn it later in number theory course. So basically we are writing, what are we writing? V sub P times n is equal to V sub n. Well, this is not multiplication. V sub P for n, and then where P is not equal to 3. This basically is saying that the amount of time amount of times p appears in the prime factorization of m. So basically, this is the power of p in the prime factorization m, and this is the power of p in the prime factorization of n. Both of them are equal if p is not equal to 3. And then b is equal to, there was p. Then we can write it as, when p is equal to 3, v sub 3 times m v3 n must be equal to 1 when p equals 3. This basically says the difference between the amount of times 3 appears in m and 3 appears in n must be equal to 1. And that's why we had absolute value. So basically, this is the answer for the question. Okay, this was a pretty tricky question actually. We had to use some early lifting the exponent lemma, which I'm pretty sure we'll teach later, but basically this is just some notation to get you started. The next question is going to be much easier. Yeah. Let's start with, I said it was going to be much easier, so let's just do this first. Okay, this is an IMO question, but this is like the first IMO question. I'm pretty sure, I'm pretty sure it's the first IMO question, and IMO is International Mathematics Olympiad, so I don't know how this got in, but basically prove that the fraction 21n plus 4 over 14n plus 3 is irreducible. Irreducible basically means that it is, like, let's say 6 by 4 is reducible, as you can reduce it into 3 by 2. But 3 by 2, can you reduce it anymore? No. So this is irreducible fraction. This is an irreducible fraction. You can't reduce it anymore for every natural number n. So if we want to make a fraction irreducible, that means numerator and denominator must be co-prime, right? So, and then we know the GCD of co-prime formula, GCD 21n plus 4, 14 n plus 3 is equal to 1. We just end with some Euclidean algorithm, right? So basically that minus 21 a comma a minus b, right? Yeah, I moved this here so you can see it as well. I forgot. Okay. So basically what we do is m, we do m minus n, 7n plus 1, and then we can also do, if we do n comma m times n, yeah, I think I'm doing it correct, I think. 21n plus 4 comma 21n plus 4, and then since 7 times 3 is 21, that's a motivation, right? 7 times 3 is 21. We try to remove the n first because n is a variable, not a number. So we try to let k is equal to 3, 7n plus 1. So and then we get 21n plus 4 comma 1. So what's your GCD? 21n plus 4. So that's basically it. We're supposed to prove that this is true actually. And then when we simplify this, the GC, sorry. Well, let's go through this again. So basically, this means we're supposed to prove that this is true, right? And then, oh, my God. I actually took the LCM. So basically, GCD, this is not LCM. So GCD of 21n plus 4, 1 is equal to 1. And that basically proves that this is true. As we simplify this into this, and we know that this is equal to 1. Right? So that's basically a proof. Okay. Now let's do another one. I think we're almost out of, oh, we have time. We didn't do this problem yet. So this also requires some motivation as well, but I think we can do this. For any positive integer n is greater than or equal to, so that n squared minus 3 and n plus 2 are always related to be prime. So once again, we all know this by the formula. We're supposed to prove this basically. This is a harder version actually from the last one we did. So basically, a motivation here is that we can write it as a difference of squares and use the generalized formula again, right? Let's do it here again. So if we write it as a difference of squares, we can let k is equal to positive n plus 2. So the best way to show it is actually by doing it. So we know that n squared minus 4 plus 1 is equal to n squared minus 3, right? So if we write that, we that n squared minus 3 is equal to n plus 2. So basically, when we have something like this, one of the good tricks is to try to make it look like a difference of squares, even if there's an addition at the end. Okay, as we can fix it later. So basically, that n squared minus 3 is equal to n plus 2 times n minus 2 plus 1. Okay, and then this is equal to, well, I guess we just apply Euclidean again. N squared minus 3 is, that's basically this. I'm just writing this as a condensed form. Then n minus 2, let's let k is equal to n minus 2. Then we did 1, right? As we did, well, let's write it out actually. N plus 2 times n minus 2 plus 1, and we said we let k equals n minus 2, n plus 2, and when we subtract, we did this crossed out, and then we did 1 at the beginning. So right here, that means now the GC is 1, and that's how we prove it. So our motivation here, and which basically trivialized the problem, is by writing as a difference of squares actually. Okay. Okay. I think maybe we can finish both our examples. Okay. I left a few harder problems out, but I think we can finish these. Okay, this one's actually a little bit tricky. This basically used the thing for, this is basically another idea. This is basically using factorizations. Like I shouldn't have just said difference of squares. It's always a good idea to use other types of factorizations. Okay, what is the largest positive integer to n for which n cubed plus 100 is divisible by n plus 10? So we're basically saying that n cubed plus 100 is by n plus n is, well, we're finding the largest positive integer such that this is still integer. So in other words, the greatest common divisor of n cubed plus 100, n plus 10 must be equal to n plus 10. So that means this n plus 10 this is basically a converse of the proposition earlier. Plus 10 will be a factor of n cubed plus 100, which basically means this. Okay. So now what we note is this looks awfully like the sum of cubes factorization. In fact, n cubed, let's say this is equal to n cubed plus 1000 minus 900. So because 100 is not a cube, 100 is square, so we make this a cube, and we borrow 900 and we write minus 900 here. And then we can also use the sum of cubes formula, which n plus 10 times n squared plus 10 times n plus 10 squared. And if we multiply it out, you'll be able to get this. Yeah. Also, I think it's something important. Minus 10n plus 100 gives you n cubed plus 1000. Let's see if that's true. Yep, if we multiply it out, you should be getting n cubed plus 1000, and we had to write minus 900 here. So this is basically equal to this, and then I think this problem is basically the same as the last one actually. Do you all know why? As we let k equals this, okay, n plus 10, n squared minus 10n plus 100 minus 900, come on, n plus 10. Then we just write the condensed form again of this, n cubed plus 100. Sorry. And then we let k is equal to this whole thing, and then we let negative 900. Actually, well, I think we're allowed to use negatives. Are we? Yeah, let's see. Sure of, I'm not sure if we're allowed to use we can have a negative on a GCD. Well, I'm sorry, but we are supposed to take the absolute value, right? Yeah, so for the formula, it's actually the absolute value of m minus k times n. So this, as we can't have a negative number in the GCD, n cubed plus 100 equals 900. And basically finding the largest n such that, well, yeah, we're finding the large, we have to maximize n plus 10 as well. And so then now, well, we're almost done. We can make it a little bit, we can simplify it a little bit more. So we just need the largest integer n, right? Wait a minute. Then make it a, yeah. Let's see if I did it correct. M, yeah, we have m here. Well, I think we can simplify it a little more, can't we? Let's see if we can. This is still a little bit confusing, right? Yeah, I think we're allowed to simplify it a little more since this is really hard to, I don't think it's possible to find a large value of n here. So basically, let's go back here. I think there's an easier way. Yeah, so basically we have all this n cubed plus 100 comma n plus 10 here. Now actually what we were supposed to do is, yeah, what we're supposed to do is actually do n minus k times n. So GC, just basically we're just flipping the value of n comma n. So it's basically flipping, right? N plus 10, and then we do k is equal to, I think it's the, I'm pretty sure you most would understand what I'm saying. So we just flip this and this, n plus 10, come on, n plus 10. Because why I'm doing is because when I did the other way around, we got something that we still have a cubic variable in, right? And then the output is a linear variable. So this basically makes it linear. Both the terms linear. So GCD, and then we do basically the same thing, n plus 10, and then we had to use the absolute value, and then we did negative 900 when you make k is equal to this, right? Wow. Okay, equals GCD comma n plus 10 comma 900. See, this is really easy. This is n plus 10. This is also n plus 10. We have to make sure to subtract 10 at the end, right? So basically, this is all we have to do is find the largest divisor of 900, and the largest divisor of something is basically itself. So 900 is equal to n plus 10. The n is equal to 890. Yeah, I'm sorry about that. We are supposed to flip it. So that's basically actually a lesson. If you try this and you did something, well, kind of messy, you did a cubic and a linear, You can try the other way. You can try flipping A and B and try doing the same algorithm again. And maybe, and you most likely you can get the correct. You can get something cleaner. So n is equal to 890. Okay? And I think we can do one more. This one's going to be pretty much, well, we have a Qmax column, but that's a really tricky one for 13 minutes. So basically we're going to do another Amy. So let R comma S, yeah, this is an Amy 8. So let R comma S denote the least common multiple of positive integers R and S. Which is basically, I think, an older way to say least common multiple, but it's still used. Find the number of order triples A, B, and C are positive integers for which A comma B 1000 LCM of B comma 3 is 2000 LCM of A comma 3. So I got LCM. Just write it all out. A comma C, we can write as. That's basically what we have now. Now let's do some inspection here actually. Let's think. And all these are in the thousands, right? So I think we can say that everything is at least A is equal, A is a factor of all A, B, and C is a factor of, is a multiple of 10, right? So first we can actually factor what I forgot to do this, but let's just do it. We can write this as 2, 3 times 5 cubed, 2 cubed times 5 cubed. This is 2 to the power 4 times 5 cubed, right? And this is also 2 to the power 4 and 5 cubed. Okay. So now we can write A comma B comma C as, we can write A is equal to 2 A sub 1, 3 A sub 2, 5 A sub 3, and A sub 1, A sub 2, and A sub 3 can always be 0. It can be 0 if it needs to. I think it may need to. We'll see. Here, B is equal to 2 to the power. Oh, C is equal to 2 to the power of C sub 1, 3 to the power of C sub 2, 5 to the power of C sub 3. Okay. Then, yeah, I'm doing correct. LCM, we just write this all out to A1. And then actually for A, does it look like it has any power of 3? This is the LCM once again. I think I like 3. Yeah. Don't have any powers of 3. My bad again. Yeah, I just made the problem much harder. Okay. Anyways, 2 to the power of A1, 5 to the power of A2, 2 to the power of B1, 5 to the power of B2. Okay. Is equal to 2 cubed times 5 cubed. Okay. LCM 2 to the power of 2 to the power of B1, 5 to the power of B2. Come on. Let's see. Yeah. Am I doing it? It's 2000, right? Yeah, it's 2000. Then we have the third one, LCM 2, 5, 1, 5, come on, A2, come on, 2 to the C1, come on, 5 to the C2. Well, now we have to do some logical. This is like a logic thinking puzzle. Let's take care of all the powers of 2 first. We'll focus on 5 soon. Okay. So for this, we can say that by the definition of LCM, X, no, I'm saying this. Okay, B max A1 comma B1 must be equal to 3. Max B1 comma C1 is equal to 4. Max A1 comma maximum A1 comma C1 is also equal to 4. Okay, now I think it should be obvious here that C1 must be 4, because if we let A1 equals 4, then max will be 4, right? And we have it 3. And since C1 does not appear here, C1 must be equal to 4. Okay, now since the C1 is equal to 4, A1 can be 18, B1 can be 18. So either A1 or either B1 must be 3. So we do cases here. And we know for sure, 100% sure, C1 is equal to 4. B1, 3, or something less than 3. A1 must also be 3 or something else. Okay, don't know that. Let's just focus. Let's do 5s now. And at 5s, well, 5s, well, these are all 3s. These are all 3s, right? And then let's think about it. We know that all of these must be less than or equal to 3, right? But it's either here, max A2 or B2, maximum A2 comma C2 is also equal to 3. And then once again, max B2 comma C2 will be equal to 3. Well, you know that something like 1 comma 3 comma 3 works. Then how about what if both of them are 1s? We say that both of them, this can be 1 comma 2 comma 3. We have two cases, either it's 3 or either it's less than 3. Okay, we know that we can have 3 comma 3 comma 3. That's one case. Right, 3 comma 3 obviously 3, all 3's work. But we can also have something like 1 comma 3 comma 3. Wait, zeros allowed? Let's see. Oh, can we also have zeros? No. Yeah, zeros are definitely possible. You can also have 0 comma 3 comma 3. As long as let's read the problem. When we are dealing with zeros, it's always best to read the problem statement again. Right? Because sometimes it says zeros are not allowed, or zeros are allowed. Okay. So basically, maximum we can't have 1 comma 3 or 82 numbers less than 3, because then when we take these two, the maximum will not be 3. So basically, we can have either everything is equal to 3. That's basically one case. And then other cases, one number less than 3. Right? And it can be 0, 1, or even 2. Right? Let's see if I'm doing it right. Okay, sure. I think I'm doing it correct. Yeah, we are allowed to zeros. Okay, and then let's go back to this one. You know that C1's going to be 4, we don't tamper with this. Okay, and then A1, either A1 or B1 must be 3. There are 2 ways to choose. This is going to use some counting. There are 2 ways to choose whether A1 or B1 is going to be 3. And then if one is 3, we have 3 ways to choose the other. It can be either 2, 1, or 0. So 2 times 3 ways. So that takes care of all the possibilities of, well, pretty sure. Well, I think let's do some casework here. So basically we need We basically need either one of x comma 1 comma x comma 2 to be 3 to count the possibilities of 1. Oh, I'm sorry. We can also have both equals 3, right? That's basically another case. 2 times 3, 3 base of 1 is 3 and another one is less than 3. And then one way of it's 3 comma 3 comma 4. It's 7 ways to choose A. And this is basically used the fundamental, and then this is independent, this is also independent, so we are allowed to multiply. For this, we have everything. Basically, we have case one, everything is 3. If so, then we have one way to check if everything is 3. The next case is either this can be 2 comma 1 comma 0. The 3 ways to choose which one is going to be 2 comma 1 comma 0. Then the 3 ways to choose whether it's 2 or 1 or 0. So that means 9 plus 1 is equal to 10. Sometimes 10 is 70. 70 is the answer. So basically, one major pitfall is here is that some people might, while solving the problem, might do a silly and forget 0 is not allowed. Another pitfall is that some people, for the first case, like me, I forgot that it was possible for all of these two to be both 3, and and then they'll give you a completely different answer. They'll give you an answer of 60, and you'll let this whole point wrong, right? So yeah, you have to like check all cases, and then once you, as I said before, if you're dealing with zeros, you should read the problem statement again and make sure it works. Anyways, I think that's the last example we have time to do today. I think we covered every example. Did we? Yep, we covered every single example, and then there'll be some more. And then yeah, there's this QMAC problem we weren't able to solve today because it was going to take a while, and it's also a pretty hard one. So the solution is there, and note that you all can use office hours. And then one thing we have that this week are called walkthroughs. Hold on, I think it's best if I can share with you. Okay, scroll down. So basically, a new thing we have today is walkthroughs. Basically, well, we don't store the solution. Well, there'll be a solutions packet, but for now we give a walkthrough. We basically tell you some stuff to do, like we let you do some. So basically, these are basically, think of them as hints. Like this is basically motivation for you, and then you try doing them, and then we don't give you everything because we still want you to still do it yourself, as you'll feel more accomplished and you learn more as well. And then if you're stuck, you can always ask us, but I think these will help. This will help you. Right? And then we have problems. Yeah, QMAC is pretty hard, but I think if we spend enough time on it, and you can also use office hours, I think it'll do fine. Yeah. Yep. We also come with hints. So you can use that. Anyways, thanks for joining today's lecture. We're on time. So hope you all enjoyed today, and I'll be happy to see you next week. Bye.
Bye.